All right. So as I said, I record a video on branch predictors. So last thing that we discussed in the class was a BTB, and just give me a second. Uh, so the last thing we discussed was BTB, and we said that essentially there are multiple different columns, multiple different structures in the BTB itself. The first thing that BTB does is kind of trying to see if this is a simple branch, and if it's a simple branch, can just find the target and move forward. And this is usually what we call a next line predictor. Then we talked about other type of branches that the other type of control flow instructions that can be used with this. One of the main one is the breadth, the return instruction. The basic idea is that each return instruction is paired with a call. So what we do is that whenever we see a call, we remember it read. And what we do is that in order to know the exact address that it needs to jump back to, we push this address into the stack. And since, for every call there is a return, we push and pop in correct order. And then it actually works very nice. This is structure usually called return stack buffer or RAS. Return address stack or return stack buffer. And then what it does is that essentially what we do is that whenever we see that this instruction is a call, then we immediately put the next instruction into uh, a return. Okay. And then there are two possibilities, right? If the current instruction is a call, then that means that we need to push into the RAS, and if the current instruction is a return, we need to pop from the RAS to gets the value from the RAS, right? As you can see, this is like in Boom Core, there is a RAS here, and then you can also see that how it's kind of like, things are getting updated, you check the branch and all that. And then if you see that it's actually like, if it's a call, then you go back and push it into the RAS, okay? So one question that you might ask is, what if we have so many calls without returns that at some point the RAS can get full, right? Because let's say I have a RAS with 8 different possible entries, and I have 8 consecutive calls without any returns. This is a very deep functions within functions within functions. So what we should do in that case, there are various options. One simple option is that you just wrap around and overwrite. What will happen is that, of course, this will lead into misprediction because essentially, remember that we always assume that call and returns are pairs. When we are overwriting, unfortunately, means that we're gonna forget some of the older, calls. But again, this would not lead to correctness issues. It's only calls to misprediction. Okay. The second thing is that you can just ignore when the RAS is full. What will happen is that then the next call will be basically incorrectly predicted. And then another idea is we can actually, if this is a recursive function, one interesting thing to do is that, calls and returns of a recursive function is always the same. So you call the same function over and over and return it to the same address. So essentially, if you somehow can just keep one entry for each recursive function, then you don't need to, save all the call and return pairs because they're essentially the same. So we can always like, just keep the last one and not keep pushing and popping the same addresses over and over again. So many of the advanced RAS designs are actually able to kind of detect this behavior and then kind of save this space with that. So that's it with the RAS. Uh, as I said, we already discussed this, but what if this is a direct jump? We check the table. If you haven't seen it before, we use the target address. And again, since this is a direct jump, the direction is not needed. It's always taken. So we move forward. Of course, not all the jumps are always in the table, which means that in some cases this is not a hit. In that case, you just don't know the address. For example, imagine the first time we see a jump address, we don't necessarily know the address, so we need to just move forward without knowing the address, and we either make some prediction or just stall the processor to know the address. So based on this, we're gonna have something like this tag BTB. As I said before, actually, we kind of discussed this before, I think the end of the last class, that the BTB has these tags. What should we use for the tag? We usually use the PC itself for the tag. But as I said before, you can actually divide the PC into two parts, into the index and into the tag. Since you're using the index to index through this table, you don't need to store that. You just need to store the rest of the address as a tag. Typically, the first two bits is also you don't need to store them because most cases PCs are multiplication of 4 because you're assuming 32 bits, so we always our PC addresses goes by 00 and then 04 and 08 and 0 C and so on. So, I'm showing it as hex numbers. So as a result, the first two bits is always 0, so there's no point of saving that either. So what you would do is that you eventually just saving this kind of like second part of the address. Why would I want to do this? Because I want to save basically this tag store, right? So the less number of bits I need to store, the smaller this the storage size will be. So I'm kind of saving on not saving this part of the address. Just keep that in mind. And kind of then the BTB becomes like this hash, this tag table and this BTB. And then if the address is there, we take it, and then the next BC basically would be that, right? Another idea that you can do is in order to basically address this BTB, there are two options that exist. Either I just directly take this index and directly index this. So for example, if it's 00, I read the first address. If it's 01, I read the second address and so on and so forth. The other option is that I can take this index, feed it into some hash function, and whatever the output of that is, use that as the index. Why would I want to use a hash function? Hash functions are helping for various different reasons. It could randomize things. It could, make sure that the size is always the same and so on and so forth. There are lots of, use cases for using a hash to address a table. You might also wonder, okay, what sort of hash should I use? As I said, if you directly use the index bits without using any sort of hashing, then you typically directly just use this. And the idea here is that you want to use spatial locality because essentially think about it this way, that consecutive addresses in the BTB will help you to store things at different tags. And you want to do that because essentially you're assuming that, sequence of instructions is going to be run after another. So you want to maximize the number of hits in your BTB. And if you want to do that, you want to kind of separate these instructions from each other. So you want to, assign one instruction to one line and then another instruction to another line. Whereas if I, for example, use the higher bits of PC, then what that means is that all of these instructions that has the same lower bits would have all map into the same entry in the BTB. So they're kind of like replacing each other, which is not a good idea. But sometimes it's usually actually a good idea to kind of use a combination of the two. So there are many scenarios, as you will see in many of these branch predictors, that use some of the higher bits and some of the lower bits. The idea here is it gives you more generality, right? So for example, if spatial locality is not always useful in your workloads and all, then using higher bits is more efficient and more effective. So you can actually use a combination of lower bits and higher bits in order to create a hash, okay? So exactly what happens is that, for example, you take these addresses, you kind of like XOR some of the lower bits, XOR some of the higher bits. That gives you a number, and this number will be the index that you're going to use in your BTB. So the idea of hashing could be as simple as just basically XORing these bits together. It could be more sophisticated, and in most cases, just a simple XORing. Okay? So then also another question that exists is what if the address is not in the BTB? There are multiple options that you can, all things that you can do. You either stall the processor entirely and saying that, okay, we don't know what the outcome is. Let's actually wait. Another option that is typically done in most cases is that you assume that this is a not taken pass and you continue. Of course, for things like jumps that are always taken, this is obviously wrong. But at least you can argue that something is better than nothing because there are some other cases that this might be true. But generally, there are like kind of two ways of doing this in many systems. Most modern processors, it's very rare that actually the address is not there. Typically, it's the first time that the address is not there. But even the first time, there are other techniques such as compiler techniques that you can actually try to prefetch the address into the BTB, and this way you can actually make sure that you always see the direct addresses. But just keep that in mind that you can also always stall the processor and not paying the price of misprediction. Okay. All right, so these are kind of the simple things. These are mainly role of the next line predictor and BTB. The more interesting part is when the branches actually has a direction, right? So you need to kind of do the prediction. So although like all of these things are technically called branch prediction, the real branch predictor is when you're predicting the direction, right? So what we need to do for that is kind of a mechanism to not only give you the address, but also give you the direction because not necessarily all the time the branch might be taken. So it's not important to just know the address. It's also important to know whether or not I should take this address. Okay. Very interesting thing about branches is that the same branch, it may change over time. So it's not like, oh, this past branch it was taken. So all I need to do is just remember what happened last time I repeat the same thing. For jumps and returns, this works very well because there's only one direction. There's no change in behavior over time. But for directional branches, the very same branch can behave differently. Think about your if then else's or your while loops and for loops, right? So these things depending on the condition, could be either true or false. And if you continuously run them, sometimes it might be true, sometimes it might be wrong, right? So keep in mind that the branches are just dynamic in nature. Okay, so now the question is, okay, that we need, a mechanism to predict the direction. What are the right strategies? And for the rest of these lectures, we're going to just quickly go over some of these options. And of course, as I said before, this is going to be used for your computer assignments as well. So there are two class of prediction strategies for direction. There are what we call static time and there are dynamic time. Static times are straightforward. There are three ways that you can use static times. The first one is what we call backward taken, forward not taken. Essentially, the idea is that any sort of backward jumps, more often than not, they're taken. And then most of the forward jumps, more often than not, they're not taken. Okay. Think about this is the way that we write programs actually. Most of the kind of like a for loop and all, these are all backward jumps. And as you think about for loops are most of the time taken, right? Because always the iterations, the variables are used for the loops many, many times it will be true, and only the last time it may not be true. And the opposite for forwards, most of the time forward branches are not taken. These are mainly like, if condition, else condition, and so on and so forth, which if you actually look at it statistically, you will see that most of the time these are not true. Okay. So that's like one of the very, very straightforward but very, very useful solutions that you can have a branch predictor that just does that. Another even simpler branch predictor is you just always predict taken or always predict not taken. Again, there are statistics that shows that uh, for various applications this is actually good enough. Another thing that you can do for the static time is you can use the compiler to profile the application. The idea of a compiler is that basically you run the application one time, okay, And you will see that, for example, which branches are being taken and which branches are being not taken, right? So you basically record the behavior of the system. You don't do any prediction. You kind of do some form of an emulation. And you say that, okay, this branch was like taken, not taken, taken, so on and so forth. This branch was like not taken, taken, and so on and so forth. So what you would do is that you kind of remember these and provide some form of a hint or in some cases what we call predicates to the processor that, whenever I see this branch, this is sort of the patterns that it needs to remember. So for example, we can store some form of a vector of bits, zeros and ones, that whenever we see that branch, we can actually use that. This means that we need a little bit more storage, but this is very accurate because essentially you literally rerun the program. And of course, if you change the inputs, this behavior might slightly change, but at least the profiler or the compiler can see heavily biased branches. So for example, if you see that the branches that are always taken, uh, regardless of the inputs, they can kind of like, hint this to the processor that, okay, this is a taken branch. You always like treat it that way. So there are lots of works on this heuristics and profiling based methods that one can use. What is actually implemented in hardware, and that's kind of like the main focus of what we're going to discuss for the rest of this lecture, is this dynamic time branch prediction. So essentially, the idea is that you can think about branch predictor as a function that takes some features and provide an outcome. This outcome is typically just 0 and 1, thinking about 1 as a taken and 0 as not taken. And what are those features that we're going to use? Features could be many different things. It could be, for example, PC address, could be branch history, could be correlation with other branches, could be other instructions, and so on and so forth. So you can use all of these features of your system. And then based on those features and some functionality that you can define, then you can basically create an outcome. The biggest thing that we typically use, and this is very popular, is this branch history. So the idea is that we want to remember the past history of the branch because the past history is usually very good indicators of what's going to happen next. As I said, for example, some of these branches are heavily biased toward taken or heavily biased toward not taken. If I can somehow remember this, then I can easily predict the next outcome of this branch. Okay? So really what happens is that the branch predictor is designing this function and designing these features. And as you will see in your computer assignments as well, what you're going to really play with is changing these features and changing this function. Sometimes you need fundamentally new functions. Sometimes you use the same function, you play with the features, or sometimes you play with what. Okay? All right, so what we do with dynamic prediction in Boom is essentially we check this bimodal predictor. The base idea is that we just remember the previous outcome and repeat it, right? So essentially, if you go back to that BTB that we have, then we can add this additional 1 bit, which we call branch history table or BHT. And this BHT is essentially instead of like just having the address and the tag, we also have just 1 bit, 0 or 1, that shows that this branch is going to be taken or not. So what happens is that for those always taken branches like the JAL and JALR and so on, that previously we discussed, we always put 1 here. This indicates that these branches are always taken. For the BEQ and other kind of like dynamic branches, we may or may not put 0 or 1 depending on like what was the history last time. BHT could be as simple as just 1 bit, and basically the 1 bit gives you like the past behavior, like the very last outcome of this branch. And the idea is that if my branch is kind of consistent, or if it's like heavily biased toward one direction, then this 1 bit would be more than enough for us to predict what the outcome is, right? So for example, if the branch is always taken or always not taken, 1 bit is more than enough to use it for prediction. But of course, you might also wonder that whether 1 bit would work in all cases, and the answer is of course no. Why? Because 1 bit essentially doesn't have any sort of what we call a hysteresis, which means that it's constantly switching between take and not take. Okay, so for example, if the last time the branch was not taken, and this time is taken, this 1 bit constantly switching between n and t and n and t. And then if, for example, your branch does not have like a singular behavior all the time, so there is no like a consecutive taken, taken, or not taken, not taken, then your prediction is not very accurate. Unfortunately, most of the time you're just predicting like incorrect. So how do we fix that? We typically add additional bits. So instead of remembering the last branch, the idea is that, okay, let's extend this to multiple branches. So for example, let's say instead of remembering the last branch, let's remember the last two branches, okay? That's how we do what we call a bimodal predictor, which has two bits instead of one bit. So for example, we can define it this way, that if I see 1, 1 or 1, 0, which means that either the last two branches were taken, or at least one of the branches, especially the older one, was taken. We're going to predict taken at this stage. So any of these two will produce a taken. This one is called strong taken, and this one is called weakly taken. And then if you have 0, 0 or 0, 1, this means that, the branch is going to be predicted not taken. These two we can interchange between like 1, 0, 0, 1, but one of them will be weakly taken, one of them will be weakly not taken. And of course, this can be a state machine, as you can see in this figure, that essentially, based on the current state and the next outcome, you can move to the different stages. So for example, if it's 0, 0 and you see not taken, you of course it stays here. If you see taken, then you go to this stage. If you again see taken, you go to like, this strong taken stages, and so on and so forth, right? So it's kind of like, this behavior you can actually, constantly switch between these states. The good thing about this bimodal is that it's slightly more resistance to fast changes. So for example, if I have a pattern like this, depending on the initial stage, there are many cases that I can predict 100% of the time correctly, right? So if I start with the correct prediction, then I can continuously predict it correctly, because a not taken will shift me to not taken stage, and then the taken one will bring me to a taken stage, and so on and so forth. So this is actually what's been largely used in many systems, including Boom. For Boom, the terminology is slightly different. So they call it a P bit and an H bit. Okay. So essentially, this is the same zeros and ones. The left one is called the prediction P bit, and the right one is called an H bit. The P bit is actually the one that we use for prediction. If p bit is 0, we predict not taken. If p bit is 1, we predict taken. You can actually look at here and you will see that that's kind of makes sense. So basically the p bit is this bit on the left. And then if it's 1, it means that we are predicting taken. If it's 0, then we are predicting not taken. So that's the bit we're going to use for prediction. And the good thing is that since it's only one bit, reading it's very fast and very easy. That's the reason that they kind of like dividing it to one bit. And then what will happen is that then we have also an H bit. We use H bit only when the misprediction occur, and the reason for this is that we want to update it, of course, and we want to update it to see which directions has to be go, right? So you want to increase, add 0 or 1 depending on the outcome of the branch. So once the outcome of the branch is known, then we update the P bit and H bit, the values that we see. So as you can see, again, we follow this state machine here. From 1, 1, we go either to 1, 0, or staying 1, 1. From 1, 0, we go to 0, 0, or go to 1, 1, or staying 1, 0, and so on and so forth. Okay. So that's kind of the idea of a bimodal predictor. And as I said, bimodal is gold standard in many of the systems. It's very simple. You can just use one bit to read things, but it has some form of a history of multiple bits. So it doesn't change too fast compared to just having one bit and one bit only. Another thing that you might ask is generally when do we update the BTB or BHD or this bimodal predictors? Usually update it when we know the outcome of the branch, right? So what we do is that we kind of like wait for the outcome of the branch, which typically happens in the execution stage for the Boom core, as we're going to discuss it later. And that's when we actually kind of like, have a kind of a feedback loop to the fetch stage to update the BTB. And when we're saying updating BTB, this includes, for example, updating the address, the target address. This could include the direction of the bimodal and so on and so forth. And then also later, as we're going to discuss, this also includes the backing predictor, the more sophisticated predictor. And then of course, if we don't have any entry in the branch target buffer when we were seeing that branch, remember I told you that sometimes there is no hit, then we can always create a new entry for that branch and move forward. And again, this happens after the fact, right? So during the fetch, we don't know it. That means that we cannot predict it, but we move forward. At some point, the outcome will be known. That's when we actually, save it for BTB for the next time, right? So the idea is that if I've seen this branch, it's very likely that I'm going to see it again. Okay. So now that we kind of know that, okay, the simple thing to do is having some form of a bimodal table, another question that comes to mind is, okay, if bimodal is just going to single bit or 2 bits going to work really well in most cases, then what are the details of that? What should we do? So there are some questions that we need to answer. For example, we might wonder that, oh, do we need a table like this for every single branch? Do we need just one table for everything? Do we need some form of a sharing or overlapping? How much history do we need? How do we address it? And so on and so forth. And that's basically the story of many, many branch predictors that you've seen in the literature. And probably some of you are gonna basically try to implement some version of this branch predictor. So let's actually talk about them quickly. There are various ideas that you can think about. For example, there are 2 sort of histories that you want to remember. The first history that you want to remember is what we call a local history. The idea of local history is that we want to see what was the previous behavior of this particular branch, okay? And this is why we call it local history, because we're talking about that particular branch. But another thing that you also want to remember, and this is also very useful in many cases, is the overall behavior of the program. Why this is important? Because the same branch, as I told you before, it can change its behavior over time. Why would change its behavior over time? Because each program goes through different phases, okay? So for example, think about a function, okay? And this function has some different condition. Let's say, for example, at some point it has a for loop or it has an if then else, okay? So what we do is that whenever I see this kind of like for loop or if then else's, this is a particular branch and I can remember the history of this branch, right? So I can say, okay, the last 4 times, these were the outcomes, okay? But think about this function. This function is actually might be called from different points in the main program. So for example, sometimes it might call from function A, sometimes it might be called from function B, sometimes it might be called from function C. And depending on which function it's been called from, this behavior might change. Why? Because typically these functions gonna send some inputs, right? So this one's gonna send some inputs, and this one's gonna send some input. And the inputs that each of these functions is going to send, they're going to be different, right? So as a result, this kind of behavior of this function and the branch within this function, it really depends on the overall, behavior of the system. That's why you want to remember the kind of the local history of these branches, including like the local history of this for loop or this if then else loop, kind of remembering what happens previously for this particular branch. But you also want to have some notion of where are we in the execution. Are we basically calling it from A or B or C and so on and so forth? And the proxy for doing that is kind of like just remembering the global history. Essentially, the idea is that I'm remembering the last 1632, 128 branches that are not the same branch from the same PC. I'm just generally remembering, okay, this is kind of like, generally we are like, taking more branches or not taking more branches. The idea is that this general idea that it can help you to locate whether you are here, here, or here. That's kind of the basic idea of this global history, okay? So based on this, we're going to have these registers. The first one we're going to use is what we call GHR or Global History Register. Essentially, global history register is this register that keeps track of last n branches of the entire program. And then the way it works is that you basically update it speculatively, which means that we don't know the outcome of the branch. Whenever we see a branch and we make a prediction, we just oops, sorry. Um, we just put a number here, and then think about this as bits, right? So 0 and 1. 0 means not taken, 1 means taken. So I'm continuously kind of like update this bits within this global history buffer, or global history register GHR, and then move forward. And of course, if we make a misprediction, we can recover it the same way that we recover other things in our processor. Using this, then we can have a mechanism like this. This is called G-share prediction or global history share prediction. So remember, I told you that we can use PC to kind of hash and then address at BTB. And remember, in BTB, I told you that instead of having 1 bit, now I can have 2 bits. Now the idea is that instead of just solely using the PC, which is kind of like give you the local history, let's now also use the global history. So this is your GHR. This is basically telling that what was the outcome of the last 4 branches in this program. It's not from the same PC, it could be from any PC. And what we do is that, for example, in this case, we just simply bitwise XOR these addresses, okay? This is just a function, it's a hash function, could be any other function you want to use, but since XOR is generally very cheap and easy to implement, most cases what we do as a hashing is just an XOR. Okay, so what we do is that the XORing these two numbers, this will be a new index. Whatever this index is pointing at, for example, let's say pointing at this point, then we're going to read the prediction bit, this just 1 bit, and that would be the prediction of this branch predictor. As simple as that. And I told you already how to update this. So essentially, we need to, after each branch, we need to update, obviously, this history buffer. And then we also need to go back and update this, BTB or this bimodal predictor. Okay. This is actually being used in Boom. As you can see, essentially this very similar thing that you can see here, that it takes the PC, it's kind of do some simple hashing, and then updating the table, and basically based on that you're gonna predict. It's very simple. It's not like really complicated. You can always, as I said before, just look at the exact implementation, look at these other kind of signals here to see what they're doing. But the simple G-share predictor is actually implemented in Boom and it's heavily used in Boom. And the hash function is also XOR. So you see hash function here, but this hash function, as I said, is just a simple XOR. Okay. All right. So what are the optimization for this? This is actually where you can actually use this idea for your computer assignments. There are tons and tons of these ideas. For example, I'm showing you one that's called G-skewed predictor. The idea of the G-skewed predictor is that instead of having one table, you can have multiple branch history tables, and you can have different hashing functions based on different combination of the global history buffer and the branch address to create kind of different indices in these different history tables. And what you do is that then you can do some form of a majority voting. So for example, if this one and this one says taken, or 2 out of 3 at least says taken, then you're going to do taken, otherwise you do not take, right? And then you can always extend this, change these hash functions, do all sort of things in order to improve. And then again, as I said, there's lots and lots of papers about this simple design, that what sort of hash functions should be used, what sort of addressing should be used, how long should be our history tables, how many tables should be used here, how should we update it, and so on and so forth. And again, would be basically what you're gonna like. I want you to kind of study a little bit about this in your free time. Think about this and try different things for your computer assignments. And hopefully you will learn a little bit more about this and you will see how it changes in your system. Okay? So these are the kind of like the simple things that, again, most of the branch predictors, even in modern processors, are using. Beyond that, there is also some more advanced schemes. I'm going to quickly talk about two of them, but there are a few others that you're gonna, again, I'm assuming that since you're gonna do kind of like explore different ideas for your computer assignments, you're gonna learn them. All right, so generally goes under the umbrella of the backing predictor in Boom terminology. So the way it works is that a request comes, the request goes to this branch predictor, this more advanced branch predictor. It also goes to your, simple branch predictor, and based on that, we're gonna provide a response. As you can see, the response is that if the BTB finds a response and happy with the response, then we basically use the response from the BTB. We don't need to, wait for the abstract predictor, more advanced predictor. But if you're not happy about that, then we need to wait another cycle and get this results. The trade-off, of course, is that this obviously is much, much more accurate. So you want to kind of consult this in many cases, but the downside is that you usually need to pay two cycle more penalty. But as I said, since branches are very, very important for the performance of your system, you're willing to pay this extra two cycles for your branches, but not paying the penalty of misprediction. Okay, so that's why it's important to have sophisticated branches in addition to your simple bimodal or next line predictors and so on and so forth. Okay. So this is, as I said, this is the idea of this branch predictors in Boom, and this is basically the part that we're gonna now talk about. So the first one that we're going to talk about is called tag geometric predictor. Different people call it differently. Some people call it TAGE. Some people call it TAGE. Some people call it TAGE. The one that I see more commonly used is TAGE, so I'm going to refer to that. But I've seen other people call it different things, especially since it's like tag geometry. People want to call it TAGE. But anyway, I'm going to call it TAGE, and I'm going to move forward. So what is the idea of TAGE? The idea of TAGE is kind of like very similar to using a bunch of different histories and combine them into a bunch of bimodals. The way that it's just using this histories is a little bit more complicated than the G-share that I told you about. So the way it works is that basically it's trying to kind of like, having multiple histories and then constantly update these histories and follow this kind of semi-complicated pattern in order to detect which one to use and which one to update. Okay, so here's kind of like the basic idea of a TAGE. TAGE usually have 5 different tables. This is like a default table. The default table is essentially just a simple bimodal. Then you have 4 other tables, and the difference between these tables is their inputs. So as you can see, the difference between each of these tables is the way that we generate the index for them. The index for them is a combination of PC plus some history. As you can see, this history are generated with this different series, and this is where the geometric part of this design come into the play. Okay, so how do we actually create this? We use this geometric series to create the histories. It looks a little bit complicated, but essentially, if you put alpha equal to 2, then basically this is the history that we care about. And most designs, we just basically follow this history. So what this says is that we're going to have history of the last 0 bits. Of course, this is this one, then the last 2, the last 4, the last 18, sorry, the last 8, the last 16, 32, 64, 128, and so on. Usually what we do is that we use some selection of this. So for example, this could be 2, this could be 8, this could be 128, and so on and so forth. Again, this is something that you can play with if you want to, okay? So going back to here, essentially now you know that this is essentially your GHR that we told you about before, but for different sizes. So for example, this is 2-bit GHR, this is 4 bits, this is 8-bit, and so on and so forth. It's the same GHR, we just pick the last 2 bits or 4 bits and so on and so forth. Then what we do, then we hash it and then select a particular table within this sequence of tables. So each of these, you can think about it as multiple tables. Within those multiple tables, then you check the tag, okay? So you check the tag and see if the tag matches with the PC that you have. if it matches with the PC, so that you check this PC with this tag. If it matches, then you use that prediction. If it doesn't match, it means that this is not your PC, you just move on. Okay, so this prediction and this tag is just basically those things. Then we also in tag we have this thing called useful counter. The useful counter is just for deciding what to keep and what to get rid of. Okay, so whenever we want to replace one particular line in the table with another line, we go and pick the one that useful counter is equal to 0. Think about it as like those of you who are familiar with caches, we have like LRU states and decide who to kick out based on the LRU states. Same idea actually kind of applies here. Okay. So why we have multiple of these tables? The idea of multiple of these tables is that we usually start from the right. We look at the longest history and see if we have. So basically, this process starts from right to left. We take the longest history NPC, see if it's a match. If it's a match, then we're basically going to use that as a prediction. We're not going to use any of these other ones. Even if there is a match, we're going to ignore them. Okay? But if, for example, this one is not a match, then we go to the next one and see if it's actually coming from next one. If next one is a match, then we're going to use T3. If T3 is also not a match, we're going to use check T2. If T2 is a match, we're going to use it. Otherwise, we go to T1. And of course, eventually, we're going to always go to T0. So if neither of T1, T2, T3, and T4 are a match, we always, fall back on our base predictor, which was like a good old bimodal predictor. Okay, so it's not like we never can predict. We always can predict at least with a base predictor. But usually the idea is that we go with higher latent with higher history. Okay. So that's kind of it for the prediction. Um, but then there's also like additional complexity to this take design, and that is how do we update an entry, essentially using this U predictor. To understand how do we update, there's two terminologies that you need to understand. There's one that's called provider component. The provider component is the one that's actually ultimately provide the prediction. So for example, if it's a match in T4, we call T4 the predictor, the provider predictor. If it's not a match in T4 and not a match in T3, but it's a match in T2, we call T2 a predictor. There's also another terminology called alternate prediction. The alternate prediction is if we use, for example, T4 for the prediction, but T4 was in fact a misprediction, but if we had used T3, it would have been a correct prediction. In that case, we call T3 the alternate prediction. So essentially, it's kind of like you can think about it is that this was more accurate and we should have used this one instead of the other one. Okay. So the idea here is that, of course, if the provider component predict correctly, then you want to reinforce that. You would increase the useful counter. If the provider predictor predict incorrectly, you want to decrease the useful counter. But you also want to kind of provide some hints for the others. That's why what we do is that we also kind of increase the useful counter of the alt prediction if it provides the correct prediction. So that's usually what we do for this updating the tag. Sometimes we also use some form of what we call an age-based update, which means that after some time, everything we decrement. The idea here is that you don't want some, very, very old, addresses and PCs to stay forever in the tag. What you want to do is that regardless of whether this branch is being used or not, you want to reduce them, you want to reduce the usefulness so that you can get rid of the old ones after some time. There are some other details, excuse me. There are some other details about the take that I definitely encourage you guys to read about it. But generally, the idea is that we just get rid, we just use this notion of usefulness in order to decide whether or not to keep this entry in the table or not. And of course, how do we replace an entry? We're going to go through the table and find the first one that the useful bits is equal to 0, and we get rid of that. And that's typically what we do for every single table. in every single part of this branch. Okay. Take is obviously implemented in Boom as well. The idea is very simple, as you can see here. I think it used only 3 tables plus a default table. Just keep in mind that this is kind of like, the way that Boom is implemented sorry, Take is implemented in Boom. And again, I recommend you to go and read the code to kind of learn about the basics of a Take, especially when it's implemented in Boom. I also heavily recommend you to read through an implementation of Take. It's actually for your computer assignments. There's already an open source implementation of Take. You can just find the code if you Google it. There are nice codes in GitHub. You probably want to use that as kind of the baseline for your design, and then try to kind of optimize it in different ways as you can see fit. You don't need to implement it from scratch, but if you want to learn, you can also implement it from scratch. Either way is just know that this exists and it's a good idea to use. Last thing I want to talk about is the use of machine learning, because as you can, for example, for now, as you probably have observed and predicted, this kind of like a feature functions outcome is a classic machine learning problem, right? So many of the existing machine learning problems are exactly the same as this. In this case, of course, the outcome is outcome of the branch. But for example, this could be used for other tasks such as classification of images and so on and so forth. In fact, actually, to no surprise to anyone, MLP, multi-layer perceptron, has been heavily used in many of the branch predictors, even in some commercial ones. The idea is fairly simple. You can think about neurons as your history. So essentially, you can think about it, okay, we have X1, X2, X3, X4, and these are the last few branches. And then I can also have some weights to kind of give you kind of the importance of each branch. Probably you want to provide more importance for more recent branches and less importance to older branches, or you can use different things. But then you combine it, and then this will result in a number. Then you can, for example, say that, okay, zero below zero, or sorry, below 0.5 or above 0.5, you can round it up or down, and that basically is your prediction, right? So it could be one layer, it could be multiple layers. Usually if it's a multi-layer perceptron, typically you go with like one input layer, one hidden layer, one output layer, or you can use any sort of other methods for this. If you're interested to learn more, how do you train this and how to design this algorithm is basically go through it. You can start with some bias weights, and then you can train it using different histories and so on and so forth. So you can actually use generate traces and use these traces, some of these traces, to train this, and then test it, of course, using the same ideas that we had before. And then typically, similar to any other machine learning, you can also need to kind of like, using your hyperparameters correctly, and avoid over learning and all that things that you do for any other machine learning programs and problems, you should apply here as well. Okay. There is, of course, more machine learning to this. Again, to no surprise to anyone. For example, people have shown that convolutional neural networks is also very, very accurate for prediction. So, for example, if you're interested in like a more heavily, deeper, neural networks and have more heavy machine learning, this is a good paper to start. But there's a whole bunch of other papers that came after this paper as well that you may want to check. And again, for your computer assignments, this could be actually a good thing for you to test, especially for those of you who are interested in machine learning or knowledgeable in machine learning. Could be an easy way to do this. Machine learning, of course, implementing in real hardware is much more tricky. That's why many systems still stick to the simple G shares or Take or so on and so forth, because They are just essentially just simple tables versus, you know, a neural network, you need to implement a lot of things and a lot of multiplications and so on and so forth. So in terms of implementation, this is a very heavy and very expensive implementation. So keep that in mind. But for your general kind of like software simulation, since you're not really designing a real hardware, you can just play with this with any sort of heavy machine learning and so on. I would be curious to see like, you know, more of a transformer based or even, you know, large language model based systems, how they would operate under this regime and how accurate would they be for per branch predictors. So perhaps something for you guys to check out. All right, so now that we have kind of learned about this, you might also wonder that, okay, can I kind of do some form of a dynamic selection between these different techniques and these different options? And this is actually one thing that's also be heavily used in machine in branch predictors. And this is typically goes under the umbrella of what we call a tournament predictor. A simple tournament predictor is kind of like, oh, I have a local predictor and a global predictor and have some form of a choice prediction and then kind of constantly switching between this global prediction and this local prediction. Another thing that you do is that you update this history and then based on that, you update your choice prediction as well. And then you can also replace this global and local with any other two predictors. So for example, you can have some form of a fancy TIG and some form of a fancy neural network, you know, predictor. And then on the fly, decide which one to use. You can see how accurate you have been and whether you want to continuously use that or you want to change that. So you can actually also have kind of a bank of different predictors, and during the runtime you can use them. The good thing about this is that, as I told you before, the behavior of the system changes over time. So sometimes, for example, your neural network predictor might do very well because of the sequence of the instructions or just somehow that's very friendly to a neural network. Sometimes the take might do well and so on and so forth. So if you have some form of a dynamic mechanism to constantly switch between them, sometimes that's actually very accurate. And again, if your system is performant enough and has enough, you know, space for different, can afford different branch predictors, that could be a very good idea to do. So that's kind of, again, going back to the pictures that I show you multiple times in this lecture and previous lectures. This is the design of the four-stage fetch unit. And now you can see that, you know, kind of like you can follow along of the whole design. We kind of covered the top part when we were talking about iCache and TLB and all that. But now you also understand the BTB, the target address, the bimodal predictor, the RAS, and now, of course, the backing branch predictor. And of course, this logic here is mainly for updating the branch and prediction and misprediction and handling all of that. So you can see that it's kind of like, you know, there are things going on to kind of like update back the BTB and so on. And again, as I said multiple times, if you want to learn specifically about Boom, my suggestion is like, you know, trying to look at their code and or look at their documentations to kind of know exactly what are these, you know, kind of like different units. The idea here for the lecture is kind of give you the basic ideas and kind of give you some examples. We don't want to go very, very deep into their design and their implementation because this is just one example of many designs. Different systems, including like many Intel and AMD processors, not necessarily follow the exactly same path. Okay. So going back to here, so now we kind of like finished with this part. Also previous lecture, we kind of talked about the decoding and renaming. Now we are kind of ready to go to the next stage of the system, which is the back end. Before that, on Monday, what we're going to do is that we're going to talk about cache and cache side channels. As I told you, is you know, an important aspect of this course is also talking about security. So the first lecture on security will be on Monday about cache channels. So don't miss it. It's important. It's very useful. And then again, this is kind of a reminder of like, so far we have kind of covered this part and now you can fully understand kind of different things here. You see that there is a BTB and there is a G-share and there is a RAS and there's iCache and there's decode and fetch buffer and decode and so on and so forth. Now we're going to kind of cover this part, this data cache part, and then we're going to move into the execution unit. Okay. Um, All right, so that's it with the branch predictor. As I said, we're gonna use this for your computer assignments. Your computer assignments is what we call a branch predictor championship. So the idea is that we're gonna give you a kind of a skeleton code. We're gonna ask you to design a branch predictor under some constraints. The constraints are defined. What you need to do is essentially improve this branch predictor. The way that we're gonna basically measure the goodness of your branch predictor is this thing called miss per thousand instructions. You want to reduce this miss per thousand instructions. Whoever has the lowest miss per thousand instructions gonna be higher in the scoreboards. We're gonna maintain an Excel sheet to show the scoreboard. You're gonna basically what you do is that you write your code in the skeleton. You're gonna upload your code to Gradescope. You can also report your MPKI on the Excel sheet. Of course, you can try many, many times and you can constantly update this. But by the deadline, we basically gonna froze this and report the top teams and so on and so forth. For grading, we're not gonna like grade you based on your rank, but we're gonna grade you based on the overall performance of your design. Your design needs to be better than some form of a baseline. As I told you before, this is also, there's a live competition for this. Our initial code going to be the older code, but we're going to also give you pointers of how you use the newer code, the newer setup to also apply for the actual championship. As I said, I'm happy to support you for like the write-up and all if you want to participate. You don't need to participate if you don't want to. You all, of course, have to submit it for your computer assignments because that's part of your grade. But if you don't want to apply and engage in the global competition, you don't have to. But it's a great opportunity, it's an exciting opportunity, so I'm assuming many of you might be interested. I also told you that you can be pair of two for on campus. For MS Online students, you have to do it alone. The reason for it is that I want to compare you against each other. And then if some of you are a pair and some of you are individual, that would not be fair. But at least in on campus, almost everyone can be in group. All right, how should you start? Of course, you should start by watching this lecture. I'm assuming that you are already watching it, so that's great. Then the next thing that you want to do is like read the code and get familiar with it. The next thing you want to do is reading some of these papers. For example, read the original take paper, read more updated and advanced papers about take, look at the machine learning base. So this predictor championship has been around for a while. You can actually look at the write-ups of the previous winners. So essentially, if you Google, you will see a lot of GitHub repos about this, so you can actually learn about that. Okay? All right, so that's it for the presentation. Sorry again that I wasn't able to attend the class on Wednesday due to travel. Hopefully, I'll see you guys next Monday. But before that, just don't make sure to start as early as possible on your computer assignments, and we're gonna hopefully publish the computer assignments very soon as well. All right, so see you guys soon. Have a good night.